All right, today we are talking about electricity, which is the flow of electric charges. Specifically, it is the flow of electrons, which are negatively charged particles. We have protons that are positively charged, electrons that are negatively charged. If you recall from chemistry, protons are found inside of the nucleus, and so they are not going to be freely moving. We have the electrons, which are found outside of the nucleus of that atom, which means that they do have the ability not only to move around that individual atom, but they actually move from atom to atom, from object to object, place to place. And so the flow or the movement of these electrons is what creates that electricity or that electric current. So let's talk first about current. This is going to be one of our variables. It will be illustrated or represented with a capital I in the formula. And it says here that current is the rate of flow of electric charges. So if you recall, the rate of in our definitions in the past has meant that we have some sort of variable where we are observing something taking place for some amount of time. So that rate of means that we are going to be dividing by time. And what we are going to be timing is the movement of those electrons. So it says here the flow of electric charges, which is really moving electrons. The unit for current is an ampere, which we normally just say amps for short. And then we will represent this with a capital A if we're using a single letter for our unit. You can see in gray that it is explaining that an amp is equivalent to 1 coulomb of charge per second, and we'll talk about what that means a little bit more as we go through the lesson today. It says here that current flows from the positive terminal of a battery to the negative terminal, or we can say that the current is going to flow from high voltage to low voltage. And again, as we progress through the lesson, you'll get more clarification as to what exactly this means. But for just kind of a brief introductory statement, you need to understand that the electrons are going to move either because of the laws of attraction or repulsion, which opposite charges attract and like charges repel. And so they need to have some sort of reason for the electrons to move or to flow. So when we are looking at an electric current that is moving because of a battery, if you think of just a battery that you put in the back of your calculator or a TV remote, we have a designated positive or negative end to that battery, and so that's what this is referring to. If we are using a battery as the source for that electric current, then we would have our electrons flowing out of the positive end of the battery and into the negative end. As we get more information today and we learn what voltage means, we will learn that this also means that the electrons are moving from the high voltage end of our battery source, and they are going to flow into the low voltage end of our battery source. So two different ways of explaining the same concept of how those electrons are going to move. Now, there will be no movement of electrons if there is no electrical difference. So when we are talking about, is there an electric current at this time? Will the electrons flow? It's going to come down to, is there a difference in the amount of electrical potential energy from two different locations? If there is a difference, the electrons are flowing. You could say in an attempt to try to balance that out, right? We've learned from chemistry that most of our nature, just kind of natural way of being for everything throughout the universe, is to be some sort of balanced state, right? So when we talk about our electric charges, if there is a difference, well, those electrons are moving to try to fix that difference or trying to balance things out. And so as a result of that, we end up with this ongoing or constant flow of electrons in the case of a circuit where we have this battery source, okay? So for our first equation for today, we have the formula I equals Q over T. If you do not like the way that the fraction is written right now with it being a slash, that's because this is something that was typed up. If you would rather express this, I is equal to Q over T, so that you can more clearly see what is in the numerator and what is in the denominator, please feel free to do that. So we have lowercase t for time, which we want to be in seconds. This is the same that we have used throughout the semester. We have capital I, which we just learned on the previous slide, means current, and that's going to be measured in amps. And then we have an additional new variable here for us. This is a lowercase q, and it stands for electric charge, and this is going to be measured in something called coulombs. That's a capital C. Now, a coulomb, if you recall from chemistry how you learned about moles and how we had this Avogadro's number, which said that 1 mole is really equal to this much, and we just kind of lumped it up to give us a smaller way to measure. So it's kind of what we're doing with our electrical charge here of coulombs. It's not necessarily one electron, it is a bundle of electrons, but we are going to say that this bundle is worth 1 coulomb, okay? And that's just because we are dealing with a lot of electrons here, and so the coulomb became the measuring unit. So we are going to measure electric charge in coulombs. So in order for us to have a current to measure, the electrons have to be moving. So what you see in this illustration is a device that is there to measure the current. So this is called an ammeter, and what an ammeter does is it inserts itself into the electric circuit so that when those electrons are flowing, they are literally passing through this machine. This machine here will get a reading of the rate at which those electrons are flowing through it, because the electrons are going to go into the machine and then out back into the circuit. So it basically becomes part of the circuit so that those moving electrons move through the device, and that's how it takes its measurement. We're going to work a couple of examples here for using this first equation. So it says here how much current is flowing through a light bulb when it takes 24 seconds for a 0.1 coulomb of charge to pass through its filaments. So our unknown variable here is current. This is what they want us to solve for. 24 seconds is going to be our time. And then here is that unit coulombs. If we write it as a single letter unit, it's a capital C. But here it was typed out with a lowercase c. So we are going to have our variable Q for electric charge as 0.18 coulombs. And that's how we would list our givens. Our formula is I is equal to Q over T. So I is equal to 0.18 over 24. And this is going to give us 0.0075. Remember, we measure current in amps. There should be only 2 sig figs here. Remember, leading zeros are never significant. So 0.0075 amps. Our next example says that a motor draws 2.5 amps. How many coulombs of charge pass through in 15 minutes? So this time they gave us the current, 2.5 amps. They are asking us for the electric charge, so they're asking for Q, and they gave us a time of 15 minutes. Remember, we cannot leave our time in minutes. This relationship is set up for our time to be in seconds. So we're going to have to take that 15 minutes, multiply it by 60 in order to put that in seconds. And that gives us 900 seconds. Ideally, you would perform dimensional analysis there to do that conversion correctly. All right, so once again, here is our equation. We have 2.5 is equal to Q over 900. In order to solve for Q, we're going to multiply both sides by 900. So over here on the right, that cancels out. We're left with just Q. On the left, 900 times 2.5 gives us 2250. So we are going to use 2 significant figures in this final answer. So we will say Q is equal to 2,300 coulombs. All right, and that's how you work this particular formula. All right, so now we're going to talk about voltage. Voltage is a word that has a couple of different ways that we could define or describe its meaning. Here it says that this is the difference in the amount of potential energy between two places. That's a typo. That's supposed to be TWO, between two places. So we have some sort of electrical energy difference that causes those electrons to move to try to change that so that there is not a difference, so that everything, all of our charges are balanced. So as long as there is an electrical energy difference, then we would say that the electrons would then be moved, or some people would say that they are forced to move. Other places, and you can see here, I also put that voltage is described as the push for those electric charges. So this electrical potential energy difference is the reason why the electrons go into motion. Voltage is potential energy per charge. So when we are talking about measuring voltage, it is a ratio of how much energy is available per coulomb of charge. So voltage is going to be a capital V in our formulas. The unit for voltage is measured in volts, so that should be pretty easy to remember, also represented with a V. So what is a volt? You probably have not heard of volts before, do not understand what that means. Again, this is a ratio of energy per charge. So 1 volt is going to be a joule per coulomb. Remember, joules is the unit for all forms of energy. Electrical energy is also measured in joules, and we've already established that we are going to measure our electric charge in bundles called coulombs. So this is going to be joules per coulomb is what 1 volt represents. Now, I've already talked about batteries a little bit, but let's go ahead and make sure that we are clear here. A battery is a voltage source. If you see this question on a quiz or a test, please do not tell me that a battery provides power. That is not what it does. Remember, power is a ratio of work over time. This is a voltage source. This is the reason for the potential energy difference that causes the electrons to move. So this illustration is actually one of my favorite illustrations of what is happening in our electric current. And I will reference this as we go through different conversations in this chapter. But we are going to use the analogy here that these little men represent our coulombs, right? That is our little bundles of electric charge. And these cups obviously represent our energy. And so when we say that 1 volt is joules per coulomb, it is the ratio of energy per bundle of charge. That's what a volt is. So when we are looking at our voltage source, that would be our battery in this case, you can see that we have our positive end, which we have discussed in a previous slide, as being the high voltage. So if we look at the picture, the ratio of joules per coulomb is pretty high because we have these little cups, which we will use to say like they're beakers, and we're measuring how much energy is available in the cup. And then we have our men, which represent our coulombs, our bundles of charge, that are going to be responsible for carrying that energy throughout our circuit. So we have full cups of energy for the men coming out of the positive end, or the high voltage end of our battery, and then they are traveling down the wire. The light bulb is on. So in order for the light bulb to be on, what has to happen is that this coulomb has to give its energy to the light bulb. Remember, light is a form of energy. So the electrical energy is now being used to create light energy. And so you can see from the illustration in this particular example, these guys are dumping all of their energy into that light bulb. And that is causing those coulombs, those bundles of charge, to exit the light bulb with no energy left in the cup. We have no energy left, or we have 0 joules, in this case, of energy We have no energy left per coulomb. We do still have our man there. We do still have our bundle of electric charges, but the amount of energy available is now nothing. And so when we have our electrons come back to this low voltage source, or what we identify as the negative end of our battery, you can see that the ratio of joules per coulomb is definitely less. In this case, it has 0 joules left. So we would have no volts left when we come back to that battery source. We measure voltage through something called a voltmeter, or in this case, they do not show a voltmeter attached to the picture, but they are simply representing for us the amount of voltage that is available throughout the circuit. So this is the same type of setup as the previous slide, except we don't have the men carrying the cups. Now they're just telling us whatever that ratio of joules per coulomb was, it came out to be 1.5. So here, our voltage is at a value of 1.5 coming out of the high voltage end of the battery source, or of the voltage source. You can see that coming out of the light bulb, our voltage has now dropped. We had a decrease in value. We can say that there was a loss of voltage, right? Because some of that energy was given away, and so the amount of voltage available is now less than what it was when it started. Now, in this particular example, we have 1.5 volts before the light bulb, we have 0 volts after. Again, that just simply tells us that all of the energy was provided to this one device. And then we come back to the battery with 0 volts, low voltage end of the battery source. So it's saying here that every time you connect something that uses energy, whether this had 1 light bulb or 5 light bulbs, or maybe this was a toaster and a microwave, whatever those electrical devices are, they are going to use some of that energy. So the amount of voltage is reduced by each of those devices. We have all of our voltage available coming out of the positive end, or the high voltage end of the battery. We have nothing left coming back to the negative end. Every single time we have an electric circuit, our electrons are going to return with 0 volts to the negative end of the battery every single time. This is a main idea that you are going to need to understand and carry in through the rest of the chapter. So sometimes we refer to this as a voltage drop, like I said, because the amount of voltage has decreased. Now, if we have a device where instead of having 1 light bulb, we have 2, I want you to understand the electrons are not going to dump all of the energy into the first device, because then there would be no energy left for whatever that second device is. So you can see from this illustration that some of the voltage gets dumped into the first object, because we had 1.5 volts, and then now coming out of the battery, this is not 0 volts, because then there would be nothing left for the second bulb. So you can see that it's some amount less than what it started, but there's still some voltage left. Those little guys and their cups, so here are those men, right, carrying the cups. Those men and their cups still have some energy left. It's just not completely full. Now they are going to dump what is left into that last device so that they have 0 volts. So coming out of the positive end, we have all the voltage. Coming back to the negative end, we have no voltage, okay? Now, is it always going to be split evenly among devices? No, it's not. When we talk about circuits later, we'll get into the specifics of that. So don't get caught up on, 2 devices, cut it in half. I just want you to understand some goes into the first, some goes into the second. By the time they've gone through all of the devices, we're down to 0 volts. Okay, if you ever have a situation where you have multiple batteries stacked up together, you're just going to add their voltage values together for your total voltage. Current is going to be flowing through the electrons. Now, remember that when we say current, we're really talking about just little electrons that are moving. Electrons are part of the atomic structure. So if we have atoms, then we have electrons. So all of our electrons are going to be moving. Do not assume that batteries provide electrons. They do not. Batteries do not provide electric charge. They just give the electrons a reason to begin moving, to begin flowing. Electrons are actually already present in the wire. So sometimes students will think that the electrons come from the battery. That is not true. The electrons are already present in the wire, okay? We have some arrows here showing the direction of that flow. So what I want you to know is that it goes out of the positive end and into the negative end of our battery source. Now, we have materials that are really good at transferring electrical current and others that are not so good. And so that is going to be the difference between a conductor and an insulator. Hopefully you've heard these words before. A conductor is any type of material that is going to allow those electrons to flow really easily. So they are good at transferring electrical current. So metals are our most common examples of conductors. Insulators are going to be materials that do not allow that electric current to flow very easily. Now, sometimes students want to say that it does not allow electric current to flow, and that's not necessarily true. There are some electric charges that still make their way through, but it's going to be very, very slow rate of movement. So sometimes we would say that nothing moves, or our observation would allow us to believe that there is no electric current because it is so bad at transferring that electrical current that we can't even tell that anything is happening, or it takes so long that during our observation time we don't see anything, okay? So we are going to define insulators as just being really bad at allowing those electric currents to flow. And then a semiconductor is a special type of material that has the ability to both act like a conductor and an insulator. And so our most common example here are computer chips. All right, so when we talk about our types of current, it's really more of the direction of flow. We have what we call direct current, and this is what we are going to see in our examples most often. This is where we have a battery as the voltage source, and because the battery has a designated positive end and a designated negative end, then those electrons are going to flow in only one direction around the current. So if this is my battery and this is the positive end and that is the negative end, then we know it's going out this way around that circuit and it's going in on the negative end. So it will never change the direction that those electrons are moving because they're always going to go from the positive to the negative. If we have an alternating current, so AC, alternating current, well, it's called an alternating current because the direction of the current moves so that it's alternating forwards and backwards, back and forth, right and left, clockwise and counterclockwise, however it happens to be drawn out. So this is going to be something like our outlets in your house. Anytime you are plugging something into the wall, that is not a designated positive or negative side of the voltage source. It actually experiences a change in the location of the positive end compared to the negative end in the wall itself. So we call it an alternating current because it is going to switch where the positive and negative side is located. And so that's going to cause the electric current. If the positive and negative on your outlet is oriented like this, well, then our electric current would be flowing, if we made this a circle, this would be clockwise. But if those current poles, flipped on us, where we now have the negative on the left and the positive on the right, well, that means that the direction the electrons are going to move is also going to flip on us. And because the polarity changes, then it alternates back and forth, and so that's why we call it an alternating current. Fuses and circuit breakers are devices that are put as part of the electric circuit in order to prevent overflow of electric current If those wires become too heated, if there is too much of an electric charge flowing through at one time, then we could have some sort of fire. That is going to obviously be very dangerous and cause damage to not only the electric circuit itself, but to whatever structure it is part of. So in your home, whenever there is a storm and you have the lights go out and you guys have to go and flip the switch on the breaker box, that is a circuit breaker or a fuse box doing its job, where it has recognized the abundance of electric current and has actually created a stoppage so that the electricity stops flowing, so that there is no fire. Okay. All right. The last vocabulary word that we're going to talk about for right now is called resistance, and this is going to be a capital R, resistance, capital R, and this is just that. It's how difficult it is for an electric current to flow through any given device, or we even have things called resistance wires that are put into the circuit that are there to slow down the flow of the electric current. So resistance is going to be a capital R in our formula, and it's going to be represented with the variable ohm, which is not illustrated for us properly. So let me, whenever I transfer, sometimes these symbols don't come over right. So an ohm is how we pronounce it. And it looks something like that. Drawing it is a little tricky for me sometimes, but this is the symbol for ohms. And you do need to know that the more devices we have in our electric circuit, the more resistance to that electrical flow. There are three factors that affect the resistance. It is the length of the wire, the diameter of the wire, and the temperature. So if you want to know what is going to create the most resistance, it is going to be longer wires, it's going to be high temperatures, and it's going to be thin wires, or they have a very small diameter, okay? So it says here the bigger the wire, the easier it is, so thin wires are going to create more resistance. All right, and then we have this equation. It's called Ohm's law, V equals IR. This is the relationship between voltage, current, and resistance. And then we're going to come back and do some example problems in a different video. We have one last equation for today, and this is P equals IV. We've already learned about power in previous chapters. This is how much energy is used per unit of time. So we originally described it as joules per second, and it means the same thing. Power, remember, is measured in watts, so we're going to have a capital P for power,